To start, pathways. Today we're going to talk about electromagnetics, which is one of the, how many, 6 areas I think that you will see throughout the semester. I happen to be the representative of the electromagnetics group. That's my name over there, Constantine Balanis. I've been here 35 years. I'm on my 36th year. So I have a little bit of a seniority. So you'll kind of respect more towards the senior. What are you laughing? That's not funny. Anyway, we will show you some things about electromagnetics and some things that we're doing. We teach a number of classes related to electromagnetics, and you will see them. All right. Now, what happened now? A glitch. It was just working just a minute ago. Let me see here. That's very nice. Well, it might be the battery, so let me check.
Put in the USB, pull it out and put it back in.
Let me try that. Here we go. Let me see if it continues. All right. So, definition. What's electromagnetics? As it's indicated there, electromagnetics is the study of the effect of charges at rest or in motion. And when charges are put in motion after you excite, put in a voltage source, the charges begin to move. And when charges are moving, create a current. A current can be DC or AC. AC currents radiate. That's how we get electromagnetic waves traveling in space and transferring information from, let's say, a receiver from a transmitter to a receiver. So the basis of electromagnetics, actually the basis, and don't let anybody else fool you, basis of electrical engineering are Maxwell's equation. Maxwell's, I'll show you in a minute, lived in the mid-1800s. Okay. So he was the one of the first to study electromagnetics and put the base of electromagnetics into 20 equations, but they were scalar because at that time vector calculus did not exist. It was shortly after his time, there was a guy, Gibbs. You probably see Gibbs phenomena in circuits or maybe in communications, came up with vector calculus. And then there were 2 other guys by the name of one guy, Heaviside and Hertz. Now you know Hertz. You know, we talk about, used to say cycles per second. Now we say Hertz per second. One also of the early pioneers. So both Hertz, after the introduction of vector calculus, both Heaviside, who was also a mathematician, and Hertz took those 20 scalar equations and put them into 4 compact vector equations we call Maxwell's equation. Now they could have named them after themselves, but because in honor of their colleague, Maxwell, they named it Maxwell's equations. Now, who would do that today? You know, come up with something and named it after one of their colleagues. So here's Maxwell, 1831 to 1879. So we're talking about mid-1800s. Scotland, in fact, and if you golfers, St. Andrews. There's a museum of Maxwell at St. Andrews, which is the home of the origin of golf, going back again to about 1400s. Now, those are Maxwell's equation. The 2 different forms of Maxwell's equation. One is the integral form, which is the one here. And then we have one in differential form. Both of them are used. I think the one in differential form is probably most widely used Now, the one over here, the first one, is nothing but Kirchhoff's law. You know, in circuits, we use take the voltage rises or voltage drop in a circle, you have to be equal to 0. Well, that's an approximation. According to this equation, they're not equal to 0. There is a term at the end of it. But for low frequencies like VHF, UHF, that term is very small. So small we're setting equal to 0. And this right here, the other one, is the node equations that we use. Currents to a given node coming in, that'll be equal to the currents what? Going out. That's in vector form. Again, this is exact. What we're using in circuits is approximate. They're leaving out one term, which is this thing right here. So the basis of electrical engineering, not just for electromagnetics, basis of electrical engineering is Maxwell's equation. So anybody, all these other classes that you're taking, they rely upon Maxwell's equations. All right. Why electromagnetics? Number one, I already mentioned. I don't think it needs more emphasis. Fundamentals and challenging problem. Wireless communications. Yes, you look at the cell phone. Actually, the Federal Communication Commission gave the go-ahead. There was a Motorola engineer came up with it. They used to call it the brick. It was about 2.5 pounds. I don't know if you. Okay. And look what it is today. This happened in a period of about 30-some years. Motorola here, the young lady here works General Dynamics. That used to be Motorola. Scott over here in Scottsdale, McDowell and McKellips and or Hayden, yes, or McClintock, extension of McClintock, basically. That used to be Motorola. Also, Motorola, actually, the headquarters in Chicago, Illinois, Schaumburg, Illinois. We had 100, Motorola had the 19 to 20,000 employees in Arizona. It was the largest employer in Arizona. They had in the valley here, they got 5, 6 different places. This was the government electronics group. And then they changed the government electronics division. We used to work very closely. We had a lot of graduate students from there. They were trying to get advanced degree, okay? Continuing education for master's, PhD. Okay, well, anyway, wireless communication, packaging of mobile units, you know, the packaging, you know, for the cell phone, or laptops. Stealth technology. We'll show you some things in there, some things that we've been doing here for the last 30-some years. We have a facility we can actually also do some testing. One of the top 2 in a university setting, us in Ohio State, this facility. Solve complex problems. Instead of using, you know, especially now with the advances in computer, instead of solving the problem approximately as lumped elements, now we solve the problems using what we call full wave solutions. Okay? And we treat the problems as a distributive. You know, you take a device, for example, and there's a capacitance and inductance and resistance throughout the device. See, is distributive. That's what I mean by solving the problem as a full wave solution, take into account all the effects. Okay. Now this part is we use a resistor, because even a resistor, even though it has 5 ohms, it has more than 5 ohms. It has some capacitance. It has some inductance. Because, you know, the packaging of the resistor, you understand what I'm saying? The wire with the resistor. Anyway, so that's what we talk about full wave thing. We have now software, advanced software, companies selling software, which cost in the hundreds of thousands of dollars to buy them. Of course, we get them free because of the university, because they want us to expose those to the students, because the students are going to work for some company or some government agency, and once they get comfortable using some software, they're going to use it. You understand what I'm saying? Modeling and simulating devices using the full wave, that's what we call them, full wave solvers. They are based on Maxwell's equations and many other problems. Here are some of the problems. Here's the stealth F-117, which It's also on the cover of one of my books, for example. Base stations, laptop, cell phone. Here's some of the insides, some of those packages. So antennas, RF, microwave circuits, fiber optics, electronic packaging, EMI, EMC, electromagnetic interference, electromagnetic compatibility, all those things, and many more. Here's some cell phones, since those, everybody's using them today. Those are some of the, kind of the first ones. This was the Motorola StarTAC. You can see the antenna was what? Exterior. There was breakage, it didn't look nice, so eventually what they did, they took the antenna and embedded it inside this package. Now you lost some performance, but it looks nicer. You don't have to worry about putting it in your pocket and then breaking the antenna. This is walkie-talkie. Now those right here, the antennas are embedded. Those are more the newer ones. Some of the ones you may have now, maybe yours might be more advanced. Another walkie-talkie. All right. One of the first questions, to be successful in electromagnetics, what do you need? Kind of essentials. You should be good in mathematics. Because probably electromagnetics of all engineering, not just electrical, in other areas, use a lot of mathematics. We saw not only scalar equations, differential equations, also what? Using vector wave equations, you understand? So we talk about vector calculus. Involves vectors. Gibbs that I mentioned came up with vector calculus. Physics. A lot of people, the physicists compared to the electromagnetics, are a little more academic. We more applied type engineers. We make things happen, you know what I mean, make it work. Physicists, they looked at systems in terms of charges moving. We looked at them as what? The lumped elements, you know what I'm talking about? Circuits, also, bases, and many other ones. So, what are we trying to do, not only here at ASU, but any other university? If you are in electrical engineering, we don't try to develop you as a technician. We want to develop you as what? As an engineer, to be able, and also be able to demand higher salary. You know what I mean? Because you'll be able to solve more complicated problems. That's the intent. So it's a little more difficult, obviously, but you can be much more better prepared when you go out and, again, have more demands at what you want to do and to join. And nowadays, there's a lot of companies looking for good engineers, electrical engineers. Electrical engineers is probably the more diversified. They can find jobs anywhere, any town, any city. Because within electrical engineering, we have so many different disciplines. IEEE, which is the largest professional society with about 350,000 around the world. Okay? Now we have another guy could walk in. He came in here to get some pizza and charge him over there $5. I mean, this guy has IEEE. We have like 35, 40 journals in the different areas of electrical engineering. You understand? Now, just in electromagnetics, we have about 7, 8 of them. We have transactions, we have letters, we have proceedings. You understand what I'm saying? So that's why I say it's very diversified. Many applications, from electronics to medicine. Wireless communication, of course, being one of the tops. Now, what are prerequisites in electromagnetics? One of the first courses everybody has to take in electrical engineering at ASU. It's the 241. I'll describe it a little bit more. It's more or less statics, not dynamics, not time-varying fields. Circuits, 202, and physics, 131, and the associated lab. Those are required by all electrical engineers. Now, so this is a kind of description of the first one that everybody has to take. Statics, and towards the end, we also do a little bit of time-varying fields, but more so, I think we expand that into the course that follows, which is 341. And prerequisites to that, circuits, 202, and physics, 131, 132. Again, here I am now repeating 241, and then this is 341. 341 is those that want to follow the EM pathway. In other words, if they want to take elective courses in electromagnetics, like antennas, like microwave courses, like optics. You cannot take those senior electives unless you take 341. If you try to take the course, you're not going to do very well. So that's one of the first things that we do in the class. That's some of us that teach some of those elective courses ask the students to make sure they have 341, because they don't want to go through half of the semester and then realize, oh, we don't have all the prerequisites that we demand that you should have in order to be able to follow the course. Then we have some other courses. Here are some of these senior electives, 443. And so when I'm teaching this semester, they're usually taught in the spring. We have two courses on antennas. This is the first one. We have about 4 courses, 3 courses actually, in microwaves. This is the first one. This is usually taught in the fall, on campus, live, not online, okay? Because now we have a lot of these online courses that are available just about any time. And this is the fiber optics course, again, senior elective course. So to take those, you need to have 341. Obviously, you have to take 241 for everybody, but for those in the EM pathway, got to have 341. Now we have many other courses at the graduate level. And a lot of those courses here that we have are not just to take space in the catalog. We actually teach a lot of those courses. Not necessarily every semester or every year, at least every couple of years. 540 is, again, an advanced course on electromagnetic computations. We call it computational electromagnetics. First course in advanced electromagnetics, 541. That's very popular. That's usually taught. We usually teach that in the fall of every year. This is 543. Now, I just taught that last semester. We didn't teach it for a couple of years. And the surprising thing was we had more students online than we had on campus. We had like maybe 18 students online, and we had about 14 on campus. First time. And the same thing happened for this one, 541. We had a young lady from a former graduate student of ours, got a PhD from me, works for Intel, been working for Intel 20-some years. She taught us she had even more online than I did. She had like 19, 20 online, and about 10, 12 on campus. So it became very popular. High resolution radar is taught this semester. 545, I guess, don't know the exact schedule, but also taught at least once a year. Professor Eberly teaches that. 546, Professor Palais. Again, this 547, Professor Pan, Professor Palais teaches, not Palais, but Eberly, coherent optics, advanced electromagnetic theory, and some other new courses on terahertz, which I have not listed here because I think they're not yet on the catalog, because in order to get on the catalog, they have to be taught at least a couple of times or 2-3 times before and Professor Trikopoulos is a new faculty member that we have. He teaches some of those courses on terahertz, much higher frequency, above millimeter waves. Talking about 600, 700, 800 gigahertz, We're not talking about 10, 20 gigahertz. We're talking about hundreds of gigahertz. All right? Graduate school. Well, MS degree. It's somewhat specialized. You know, you're not going to advance the world. You know, you're going to take a topic and you're going to research it, and it might be an existing topic, and you're just going to advance it, do it a little bit better. And you write now we have options. One is without a thesis, you take 30 courses instead of 30 hours, not 30 courses. And you don't have to do a thesis, but you have to take an exam at the end when you decide to graduate. Right? But there's one option with a thesis. The one without a thesis, it's MEE. Yeah, I think MEE, right?
MSc.
MSc. MSc. So we have MSc is the one without the thesis. Okay, and then we have the MS. Yeah, now I got it straight. Well, when you get older, you have a tendency to, I don't want to say it. MS. That one, you take at least 4 hours of coursework and then 6 hours for thesis. Now, thesis takes longer than 6 hours of coursework. But at least you get an opportunity, especially if you intend to get a PhD, you learn how to take a topic, research it, communicate it both orally and in writing. Very important. Okay? You have to develop communication skills, because people think that the engineers cannot talk, cannot communicate in writing or orally. That's a good opportunity to show them that we can. And it's more, again, applications oriented, most often marketable degree for pursuing a career in industry and government. Although today, you'd be surprised, people in industry and government are looking for PhD. Excuse me, PhDs, not for masters. Maybe 10 years ago, that was the #1 degree, master's. Now, look at the Intel over here. Has hired quite a few of my graduate students. They're all PhDs, because they're working on more advanced problems. And more advanced problems, they need more advanced skills. And what do you get the more advanced skills? Pursuing higher degree. All right, PhD. It's very specialized. You're going to take a topic and you're going to research it, and you're going to become, quote unquote, the expert on that particular topic. You should know more than just about anybody else, including your advisor. It is true. It should be true, because we're advising a number of students. If we know more for each one of the students, maybe we should be Einsteins. We're not. You understand? So you take it, that'll be very detailed, and one ends up knowing quite a bit about one area topic. It's more a research and development. Again, as I said, companies, government, national labs, Lawrence Livermore Laboratory, San Diego Corporation, all those, hire people with advanced degrees. And ultimately, if you have any aspirations to teach at a university, college, university nowadays, it's a must. Certainly universities, even colleges, you have to have a PhD degree in order to be able to get a job in academia. So here I am, I guess, kind of premature. I already alluded to this. Academia, I need a PhD. Industry, bachelor's, master's, PhD. People used to say that, well, get a master's degree. That says a lot of the companies don't want a master's, that bachelor's is good enough. Well, that was not quite true. They didn't want to pay the money, because a master's degree would demand higher salary. PhD will demand higher salary. So I don't know if you guys checking on salary structure. I had a young lady in my class last semester. She's going to go work for Microsoft in Seattle. through her boyfriend, he was also in my class, told me she got a bachelor's degree, $109,000 plus $75,000 in stock options. Okay? Bachelor's degree. All right? So keep that in mind. She was a good student, also, by the way, I should say. Industry, number of companies. We have a lot of companies here locally, kind of after Silicon Valley, maybe Boston area. I think this is maybe one of the top three. Silicon Valley number one, maybe number two, number three. Remember when I said Motorola had 20,000 people here. Now we don't have hardly any now from Motorola. Honeywell locally, Boeing in Mesa, General Dynamics, let's see, Rockwell International, Raytheon in Tucson, Honeywell in the northwest part of the valley. Qualcomm has a small group here. United Technologies, Bell Helicopters, Andrew Corporation, I don't think this. And then you have the Army Navy, Fort Huachuca Army, down a little bit south of, and I worked very closely for them for almost 28 years. We're sponsoring some work over here. So you have many opportunities. And those places, Army and so forth, have many installations throughout the country. There's not just one, not two. Navy, same thing. If you go to California, San Diego, Spaywar is there. Now, the laboratories that I was telling you, some of the things that we're doing when I came here, this is what we call the electromagnetic anechoic chamber. When we make measurements for antennas and other devices, we don't want any interference. Okay? Now you can do this in the outside world, outside of buildings, but then you have a lot of obstacles. The weather doesn't cooperate all the time. So it would like to be done in a controlled environment. Of course, if you do it indoors, you have the walls. So what you can do is we have materials we call RAM, radio absorbing material, like the ones here, they look like cones. What they do is we line up the walls, all the walls with this materials, and what they do, they absorb. When the electromagnetic waves comes in, it absorbs it, it converts it to what? Heat. Just like we do where? Everybody has one of those devices at home. Microwave oven. That's the principle of a microwave oven. Now, the heat over here, if it was high intensity, power high, it will burn. But of course, we're working on lower power levels. And that's why those are designed in such a way, pyramids, in other way to provide a smooth transition from free space to this material. Instead of being flat, you go very gradually, smooth transition, like a cone. It's probably one of the smoothest transition type of a design. And again, this is one of the, we built it in the mid-80s. Again, one of the top two in a university environment. Companies have. And we built this with basically very little money. We got some money from the government. ASU kind of matched the funds. This, at that time, if we had to pay for everything, it would have been maybe $7-8 million. We built it with about $500,000-$600,000. We got a lot of donations. Okay, our facilities here in the College of Engineering, the people, we took them to Motorola to see a facility like this, and they learned, they saw what it is, and they did it. They actually put this absorbing material on the walls. We did it ourselves meaning ASU people. So it's one of our distinguished laboratories. And up to date, we make precise measurements of antenna measurements, what we call RCS, radar cross-section. That's the one for stealth technology, which I'll talk in a few minutes. We have some other labs. Wireless communication lab, mixed signals, to those of you that may be taking classes or maybe pursuing degrees in the areas of circuits. And there's also one of the measure the material properties or the properties of materials. That's very important because when you model something and you use some kind of a dielectric material, you need to know what the properties, what properties. We call the constitutive parameters: permittivity, permeability, conductivity. If you don't know those properties of material, you can't model the device, whatever it is. So sometimes because manufacturers don't have a precise information when you buy something like that, we're testing them in the laboratory. There are techniques you can measure and determine what are their values. Not only the values at a given frequency, but over a frequency range, because a lot of the systems don't operate at a single frequency. They have a bandwidth. Just about every system operates over a bandwidth. Now, faculty. We have a faculty here. Professor Eberly has been around here for quite a few years, maybe 30 years or nearly that. I'm on my 36th year. He's the, what do we call him? It's not nice to say oldest, but more senior. Not only senior in age, but also senior in service at ASU. I think he came here in the 70s. Okay. Professor Pan came later, and the newest one of all is Professor Trikopoulos. He's been with us for about 2-3 years now. He's the one he's more into terahertz. Some of these people change faces or the way they look, long hair, short hair, whatever. And here's one of them. I think now he's got long hair, I believe. You may not be able to recognize. But anyway, Professor Eberly teaches a lot of our courses in even in circuits, electromagnetics, microwaves, and you can see his degrees and exactly what he's doing. And I'm sure before you leave here, you're going to take at least one course from him. Yes, sir.
Isn't he also the faculty honors advisor?
He's also the faculty, one of them. I think we have more than one, I believe. Am I correct?
He's the main point person, you're right.
He's the main contact. There you go. That's why the ladies came here to back me up, even though I accused them of came here to eat. But I think they're very valuable, obviously. Yes. Here's some of the things that he's doing, what they call non-Foster circuits. He's more involved into teaching now, I think, more than research, although he's pursuing research with graduate students. He has Professor Trikopoulos with some of the, I think he'd be able to describe those things better than I can. He's very active. He has a number of students, graduate students, that are working for him. And last but not least, that's an outdated, maybe I don't want to bring it up. Huh? Anyway, again, came here to ASU 1980. I've been teaching for 49 years. This is my 49th. Maybe I'll make it 50 and then I'll tell you goodbye. Don't cry, don't cry. You probably have a party, you have a band that says, let's get him out of here. I'll show you a few things as time permits. I know we already to 40 minutes. Let me show you a couple of things to open up the discussion. I can show you more. And there's Professor Pan, he graduated from University of Kansas. He's a computational electromagnetics packaging. Was more active in packaging when he first came here, rough surface scattering. That's part of his, I believe that was part of his dissertation at the University of Kansas. Professor Palais got his degrees at the University of Michigan. a PhD. I think he got a bachelor's degree, I believe it. And I don't want to mention it, University of Arizona. But then he saw the light, and I think eventually ended up at ASU. Okay, he's been here. I believe he started his teaching career at ASU late 70s, something like in the 70s for sure. I started mine in the 70s, but I started at another university 13 years before I came to ASU. So maybe he and I started teaching about the same time. This is some of the courses that he's teaching. Primarily nowadays, he's also the academic graduate advisor. And so research-wise, I think he's more, actually, he has already retired. He's professor emeritus, but still spends his time here. I think he was doing advising in graduate studies and also teaches some courses, primarily optics, lasers. Those are some of the ones, topics of research interest right now. I had a consortium, government agencies, and industry for 28 years. We started in 1990. We just sunsetted this past November, 28 years. Now we have a contract with the largest research center from Saudi Arabia, CAX. There's a King Abdulaziz City for Science and Technology. Now, let me just show you the thing because of time constraints here, what we're doing related to radar, okay, and antennas as well. If you have a flat surface, metallic like this, and you have a wave coming in here from the radar, most of the energy goes back to the receiver. This is very visible to the radar. So there are a lot of things that you can do to try to make it more stealth, to make it less visible, to have a lower radar visibility or signature, as sometimes they refer to. One thing that you can do, if you look at this F-117 Nighthawk, shaping. You can shape the thing in such a way that when the wave is coming in, hits the target, the structure, it directs the energy away from the receiver. So one is shaping. The other one is you can cover it with material. Just like when we talk about the absorbing material on the walls, such that when the wave hits the structure, it traps the energy within these materials and converts that to heat, then very little coming back. So materials is the second one. Well, more recently, the last few years, we were able to develop surfaces, different architectures, like the one I'm showing over here. We put little patches on them. We call it the mushroom, because it looks like a mushroom surfaces. We have a metallic surface, we have a dielectric layer, and put patches of different shapes, and also some separations between them. They have to be designed properly, okay? You just can't throw anything in there. And what it does is takes the incoming wave and directs it away from the receiver. For this one here, it creates 4, let's see if I can get to that very quickly here. I don't want to get through the, see, if it was this side over here, perfect conductor, if it's coming in this way, most of it will go in that direction. You see the main lobe over there? But when we do something like this, which is this one here, the exact one, okay, what it does, creates 4 beams away. The receiver is over here along the z-axis, away from it. So this is acting as an array of elements. You excite currents in such a way, and phases in such a way, which are separated from each other, each element, that forms what we call an array, antenna array, and is such that it provides destructive interference towards the receiver, but constructive interference away from the receiver. so it becomes less visible. Now, another design, and we have many of them, I may have it. So you can see there, the 4 quadrants where the maximum was redirected towards. Now, the other one is hexagon. There's one right here, and I'll show you. This is the actual thing. This one, because instead of being rectangular, is hexagonal, 6 beams. Same thing. Obviously, you take the same amount of power, instead of split it into 4 beams, into 6 beams. Each one of those beams, even the maximum intensity is a little bit lower than the ones with the 4 beams. Right? Again, bistatic RCS, or RCS stands for radar cross-section, is the parameter which kind of tells you how visible the target is to the radar. That's what they use as a figure of merit, to decide on the visibility or on the signature of the element. Then you can make them, this one is very similar to the first one, except some of the patches are a little different. The dual band, instead of being just a rectangular patches, the rectangular patch with a little loop in the middle. It has double resonance, and it gives us a little more broad bandwidth. And one more, and then I'll stop and try to answer questions, because I have a tendency, I like to talk, as you can tell. They're laughing. He says, don't tell us something new. If you happen to have non-rectangular geometry, less circular, see, the patch is a little bit different. That's what this one is. Okay. And many other ones. We have students here, been with us for a while, that we have published, we've been funded from industry. And so those are some of the things that we're doing lately. This is one of the most active areas that we pursue presently. Now, remember, as I said, I started in 1970 in teaching, so I worked with the microwave landing system that I mentioned, the airports, to land the aircraft. It used to be the ILS system, which was in existence for 40 years. Then the FAA decided in the early 70s to design a higher precision, high resolution landing system in the microwave region, about 5 gigahertz, actually 5.1 gigahertz at that time. Then it went to free known. Anyway, they call it the microwave landing system. More precise, they could land aircraft even with zero visibility. I worked back then. So those are topics going back to the 1970s. So last, let me show you, I did show you the facility. Well, let me go over here. Ta-da-da. You see, this is the one I was showing you just now, and last, and this is some antenna work over here, kind of similar. Those are synthetic surfaces, because a surface which has this kind of characteristics doesn't exist in nature, is not part of the periodic chart. So these are here synthesized surfaces which mimic the characteristics of surfaces which do not exist in nature. You understand? Okay. They're synthesized. And also we've got to do a little bit of advertisement. Right? Commercial. Okay. Our faculty have published some books. This is mine, 3rd edition, 4th edition. This is the latest one. This is in color. That's the one we use now. This is the 2nd edition of the EM book, and you can see I got the F117. I had to get a permission from the company in order to use that. I have a small book on smart antennas, handbook. Actually, I was the editor of this one, and we got like 20-some chapters written by different people around the country, around the world. This is a book by authored by Professor Ballet on fiber optics, and this is a book on wavelets in electromagnetics, computational electromagnetics, by Professor Pan. So, with that in mind, I will stop at this point, and thank you for listening. and I would be happy to try to maybe entertain any questions, see if I can answer them. So I think you're ready for a question, I can see. You're not?
No.
Well, you told me you came here to listen, not only to eat, but you came here to also ask questions. So you forgot the question?
No, I didn't have a question.
Then, yeah, I know the young lady here. She works for. All right, what?
What classes, if I'm doing communications at General Dynamics, which classes would be best?
Well,
Like RF receivers, transceivers.
well, I don't know all the communication classes, but certainly if that's what you're going to do, you take a lot of communication. But you should take something because the communication system is not just one area. Okay, if we look at the wireless communication system, there might be 7, 8 different disciplines within the including controls, if you can imagine, feedback loops and so forth, okay? So you should take the communication courses, signal processing, but I think you also, again, not because I'm in electromagnetics, antenna courses, I think would be appropriate. We've got a young man over there, he's in class right now. He can tell you, he can urge you to, recommend that you take it, or he may say stay away.
No, I would take it.
Yeah, I would take. They're kind of related, communications and EM, some of the microwave courses. Yeah, okay. Because microwave system, you have to put them together, you know what I mean? Devices and so forth. So that's what. Now, I don't think you should take courses. You could, if you have an interest in power. Those are not quite different from each other.
Yeah.
And people in power should not take courses in electromagnetics, although actually in power should take a course in electromagnetics. Discharges, corona discharges and so forth, they're all the high-powered electromagnetics. So, all right? So we're, all right. You in class? Okay, now let's, any questions? Don't you? Oh, let's since you're kind of bashful, you don't want to ask a question. I know you have questions. Yes, sir.
Between the two masters, is one more prestigious or make more money than the other between the MSc and the MS?
Well, I don't know. I don't have the statistics on that. I would think, personally, okay, the MS would be more because I think you're going to provide a document. You're going to take a topic, you're going to research it, you're going to learn, how to take a topic, research it, and then be able to communicate both orally and in writing. So I think it's a learning process. Yes, you're going to spend more time. They give you 6 hours, credit for doing the thesis. Well, you can take 6 hours in one semester and done. Right? But I think the learning process, especially if you're going to work for a company, they're going to ask you to write a report, write a proposal to get funded, let's say from government, national labs, or whatever. So, and that's my opinion. Now, somebody else may say something different. So, I did a MS. Even though mine says ME, actually I did a thesis because the university that I went to, they didn't call it MS, they called it ME, but it did require a thesis. So, it was a learning process for me.
All right, thanks.
Mm-hmm. Somebody else over there had a question. Yes, sir.
Which staff for electrical engineering is focused on power systems?
I'm sorry?
Do you have any staff or instructors that have a focus on power systems?
Oh, absolutely. In fact, in our department, we had two of the faculty in the power area were National Academy of Engineering. One just retired, he's a professor emeritus now, but the other one is still here. So yes, we have one of the top, maybe if not the top, group in power systems here at ASU. The other schools would be like Purdue, Texas A&M. So yes, we do a very strong team in power engineering. And I'm sure somebody's going to come here eventually, I think, to address you in the power area. But I would urge you that you switch from power to electromagnetics. He's not convinced. He's not laughing. So he says, no, he's stuck. He's going to stay with power. No, we have some power companies here locally, SRP, And I think they hire an engineer. They work very closely with our faculty, I believe. Yeah. Yes, so we have a very good, excellent power group. Okay? Others? Yes, sir.
Would you say this is the most mathematical of the emphasis areas?
The most mathematical?
Yeah.
Electromagnetics? Yes, I think that. And if you look, beyond electrical engineering, I think aerospace engineering, they do a lot of stuff in aerospace engineering. Not mechanical, aerospace engineering. They also use a lot of mathematics. But I think we may be the number one. Just ask me and I'll tell you.
You sound biased.
No, unbiased. Because we use, vectors quantity in addition to scalar. If you go industrial, mechanical, a lot of the stuff is done in scalar equations. We use, when we have a vector wave equation, you have to break it, in order to solve it, you have to break it down into 3 scalar wave equations. Where when you have one scalar equation that they deal with, you only have one. Okay? And you have, vectors rotate, you have a polarization. It's more complex, I guess. I don't want to scare you. I just want to tell you the truth. Because I don't want you to come to class and they say you'd be disappointed. It's more challenging. And if you want challenging, then come to electromagnetics. Somebody else had a question. Yes, sir.
Would you suggest either after getting your undergrad, receiving your going to get your master's, or going to work first and then going to get your master's?
Excellent question. Yes, yes. I was in that. We all were in that position at one time or another. Okay. My recommendation is to go ahead and. I graduated, we couldn't wait to graduate. We used to count months and then weeks and then days and hours. No sooner I graduated, I worked for NASA initially for 6 years. I couldn't wait to get back to class to pursue so I started master's degree almost immediately. Now what happens is, once you start working, you make money. And then maybe some people have families, develop families. And first of all, more obligations with family, right? You have to, the wife is going to say, oh, you can't do all this stuff, to study all the time, da, 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 da. So you have to have an understanding family. That's number one. Number two is you start making money. Okay? And let's say a bachelor's degree, maybe today 80,000 plus or minus, somewhere in there. And to become a graduate assistant, making about $900 a month. You understand what I'm saying? But you're going to make up that. The money is going to catch up eventually. Because you get an advanced degree, you're going to make more money. And also then, and another one, which I have seen with people, competing with different generations. If you stay out too long, some new advances, some new material that we teach in class, some new classes are introduced. You missed out on those when you got your bachelor's degree. So now you're competing with younger people, more up-to-date, more advanced methods. Now, it doesn't mean all of those are going to happen, but it could. So I went basically straight through. Get it out of your system. Don't have to worry about a weekend. He says, should I study, or should I go watch a ball game, or should I do this, should we go play golf, or whatever you like to do. Get it out of the way. Well, you're still going to be thinking, I can tell you that, because I'm still thinking about it. Depends on the person, of course, okay? You feel guilty to say that I'm going to go do this when I should be studying because I got a test coming up. And no matter whether you take in one test, in one class, because you can do it on part-time. To me, whether I took one class, 2 classes, or 3 classes, it was always in my mind. Should I go out or should I study? Okay? So my advice is straight through. You're poor, stay poor. Well, until you finish. You know what I mean. And a lot of opportunities, we have a lot of support to graduate students, the graduate research assistantships and so forth, teaching assistantships that we have over here. And sometimes we can't find a good student. If you're a good student, it shouldn't be any problem to get a graduate research assistantship. I say good student.
To build off that, do you find value in getting your PE, or is that solely off the company that you decide to work for?
I think I don't have a PE, and I never did even consider it. And I've done a lot of consulting. I've been in the court, in court as a technical expert and with the international companies. Okay, in some areas though, like young man they mentioned power. I think most of the people in power, I think usually the more professional, get their professional degree accreditation, whatever you want to call it. Yes. But in some other ones, I know a lot of my colleagues here, I don't know too many of them that are professional engineers. So I don't think, unless you can go in some area that do required, most of them do not require that you have. I was never asked, show me, in other words, for me to participate as a consultant and eventually to appear in court and so forth if I had a professional engineering accreditation. And I've been around for 49 years. Okay? Any other questions? Did you enjoy the pizza?
Oh, yeah.
Huh? Would you have come if there was no pizza? Would you have come?
Yes.
Yeah.
Come on, be honest. Because we're trying to cut down on expenses, and we thought maybe if we cut down on pizza, maybe we may save more money.
We needed the pizza.
Oh, we needed a pizza. That's what I thought. All right. Well, I appreciate you guys coming, listening, and hopefully we'll see you maybe following semester. Okay? Thank you. Thank you very much.